Hello, and welcome to Week 1, Lecture 3 of CO 442-642 Graph Theory, a writing example. Today we're going to be going through an example of poor writing and how to transform it into better writing, to learn how to use those writing guidelines we learned about last week and put them into practice. So let's go ahead and dive in. So here is our example. Suppose we want to try to prove the following theorem. Every two longest paths in a graph intersect. A very simple problem that we often see in Math 239, and now we'll try a proof. So here's an attempt at a proof. Let's go ahead and read it together. If there were two longest paths that did not intersect, then there must be a path connecting them. By choosing the longer paths of the two paths together with that path, we can construct a new longer path than the original path. That's a proof, right? Well, let's ask that question. Is this proof correct? Go ahead and pause and think of your answer. You can study it if you want. So what is the answer? Is this proof correct? A lot of you would probably say, no, it's incorrect. I would contend actually that it's neither really correct or incorrect. Rather, it is too imprecise to even determine its correctness. So maybe let's actually ask what's wrong with this proof. So, I've said it's imprecise. In what ways is it imprecise? So go ahead and think about the various ways. I have a whole list of them, so there's not just one answer here. But go ahead and pause the video and think about all the ways in which this proof has violated those writing guidelines, and it's too imprecise. Go ahead, I'll be waiting. Okay, so now that you've unpaused and you have all your answers, let's see how many of your answers accord with mine. So, no particular order, I'll just go ahead and mention some. One is the use of the subjunctive. It's everywhere there. It's at the beginning of the proof. If there were, that was one of our examples. There is a must in the middle. There must be a path connecting them. We can construct. All uses of the subjunctive, all ambiguous. So, of course, we could just try to get rid of all those, but there's a lot more going wrong with this proof. There's the lack of labels and the resulting ambiguity. What subpaths are they talking about? Which path is that path? There's a lot of ambiguity going on. There's also no beginning. Is the proof direct or is it by contradiction? It seems like it's by contradiction, but we were never told that. Similarly, there's no end. How do we know we are done? And then the construction's also unclear. What does together even mean in this context? It doesn't explicitly say how you put these paths together to get this supposed new path, so that should probably be cleared up. And actually, the more you undo all the rest of that, you'll begin to see the arguments themselves are missing reasons. There's really no reason clauses in any of this proof. So to actually understand how the arguments work and why they work, those key reasons turns out will be missing. So there's a lot wrong with this proof. It's just a vague sketch. It's not really incorrect per se. It has a certain right idea, but there's a lot that needs to be cleared up. So this is again an example of bad writing. Even if you think you're a good writer, it's helpful to be able to diagnose poor writing, or rather this imprecise writing, and to figure out all the ways in which it can be fixed, especially if you're going to be a graduate TA for an undergraduate course, to be able, or just to help friends with their writing, or to analyze your own writing, to go back and be able to see what about my writing is imprecise. How can I change it to be better? So let's do that for the rest of this lecture. How can we make this proof better? How can we make it more rigorous? And of course you might just say, well, this proof is just terrible. Let's just throw it out altogether and start from scratch. And we could do that. Sometimes proofs are so awful we should. But here I'm going to try and take it step by step and improve it one aspect at a time. So how do we correct this proof? Well, let's maybe, you could stop and you could think about it, and there's a lot wrong, but let me maybe contend that we should start at the beginning. So let's add a beginning. That seems the easiest way to begin. Add a beginning, right? There's no beginning to this proof. That was one of our guidelines. Every proof needs a beginning. Is it by induction? Is it by contradiction? So let's go ahead and do that. So let's add suppose not, right? It's by contradiction, so suppose not. And I find it useful if it's by contradiction, start with that, and then say what the suppose not is. So that here would be, that is, there exist two longest paths that do not intersect. And then you can continue. Then there must be a path connecting them, and all the rest of the poorly written proof. But at least we have a beginning now. We've said that these two paths are because we're doing this contradiction. Okay, what next? Well, we label. Do you remember that from imprecision? Our guidelines. So we label, right? That's the issue. There's just no labeling, like especially at the beginning there. What are these two longest paths? So let's go ahead and label. So let's say longest paths P1 and P2 that do not intersect. And I'm going to go ahead here and say, well, now that we've actually given the names, instead of being a bit wishy-washy with do not intersect, we can actually just precisely say what that means. We can say such that V of P1 intersect V of P2 is empty, right? That's what we meant by not intersecting. So we've gone ahead and add that, and then while we're at it, we might as well for the next sentence say then there must be a path P connecting them. And we can continue like this, but I'll kind of pause there because there's a lot more going on with the rest, these subpaths, what else. So we will end up labeling those, but this is a good start. We've at least labeled those first couple sentences. But then what? Well, the next thing while we're reading, I find in that next sentence is must, right? That was one of our no words. So we have to fix must. And there must be a path P connecting them. And so I'd ask, what is the purpose of must, right? This was one of the things about must, even if here it's more emphatic and imperative than a subjunctive, but what is its purpose? Is it telling us that obviously this is true or that it follows from known things? And so I'll let you think about that for a moment. What is the purpose of must here? Well, I'd argue it's probably emphasis, that it's saying then there is, so we could probably just replace it with is. Then there is a path P connecting them. But that begs the next question. Why is there a path connecting them? I mean, and also what does connecting them mean? I assume they mean that by that rather unclear phrase connecting them, that one end is in P1 and the other is in P2. So they should have said that and been more formal. So that's the use of informal language there. But why is there such a path? So again, pause the video and try to figure out why is there such a path connecting P1 and P2. Okay, so I'll assume you're back and you know the answer. The answer is, well, there does not need to be. There does not actually need to be a path. This is actually a lie. This is incorrect. It was hiding this incorrectness behind that must. Right? Must just makes you want to believe it so much you don't question why it's true. If it was is, we might have thought about it more, and now we have, and we realize, no, there doesn't need to be a path. Why doesn't there need to be a path? Because the graph doesn't have to be connected. Right? If these two longest paths lived in different components, then there would not be a path with one end in P1 and one end in P2. So actually the whole statement or thing we were trying to prove, our theorem, is just false. That proof was just a false proof, or rather it was a correct proof of a false statement, or rather a very imprecise one. So we should first modify the statement. So that's what we'll do. Here's a second attempt. Theorem. Every two longest paths in a connected graph, G, intersect. And I'll go ahead and label it G just for the ease of the proof. So in a connected graph G. Okay, now you could go back to that original proof even, read it again, and now you actually might say, actually that proof is kind of right, it's just imprecise. So if your complaint on the first slide was, well, obviously this statement is wrong, what is Luke doing, and why doesn't he have connected? Well, I was waiting to expose this to you, but that's not really the reason the proof is incorrect. Yes, it missed that point, but the proof would, this imprecise proof would work equally well for this actually true statement. And that's kind of the point. That actually a very imprecise proof can work equally well for a false statement and a true statement. And it's the imprecision that's the problem. So we need to continue working, turning this imprecise proof and now into real proof of this actually true theorem. So let's pick up from where we were in here, and for the rest of the talk, I'll make the font a little bit smaller because our proof is going to get much longer from that imprecise version. And so we'll pick up from where we left off. So suppose not, that is there's two longest paths, they don't intersect. So here I'm going to add, there exists a path P from V of P1 to V of P2, and that should be clear then instead of connecting them. But here I might as well add the reason, right? Now that we know it's not always true, it's because it's connected, I can go ahead and add that since G is connected, there exists a path. So we fixed that part. Good, solid beginning, right? But now, the next part. We have to continue on with the corrections. What about these subpaths? Well, let's label the subpaths. So let's go ahead and do that. So then it gets a bit messy. right, I'm going to need to talk about the ends of P. So I'll need for each I in 1, 2, we'll have to have ui be the end of P and v of pi. And that's actually, if you think about it, unique which end it is because they're disjoint. So that'll be fine. And then for each ij in 1, 2, we'll let qij be the subpath of pi from ui up to, well, this is where I need to label the ends. So actually, if you notice in the proof, I went back and I wrote for each I in 1, 2, let vi1, vi2 be the ends of pi. That's to be able to then talk about what these qij should be. So I add that in, and then I do ui's, and then, so I'm entering things into elements, the ends of the path. So we're going to need them later. We didn't really need them, but now we realize we're going to need them later. So when we introduce them, we might as well give names to their ends. And then the same for, we're going to need the ends of P, so we'll name those, and then we'll need Qij. And we could have just called them, Q1, Q2, Q3, Q4, etc., whatever you wanted to name them. But here with the Ij, it's a little easier to apply with loss of generality arguments, so that's the way I'm going to do it here. So we've done that. Good. We've labeled the subpaths. But we still have to fix the argument, right? So we have to clean up that last part by choosing the longer subpaths. So let's do that. So instead of, two paths together with that path, so we have to talk about which one's longer. So we assume without loss of generality that EQI1 is actually bigger in size than EQI2. So that kind of tells us, we're assuming without loss of generality that the j equal 1 sides are the longer such paths for each I in 1, 2. And now we can actually just directly write what the path was, that path. It's just let P prime B go from V11 down Q11 through U1 through P1, that should be P, through to U2 up Q21 and then to V21. And so that's the definition of the path, sorry for the typo. And then we add an ending. So what is our ending? Well, we should say then P prime is a longer path than P1, contradicting that P1 is the longest path. All right, so that's our end, right? Contradicting that P1 is the longest path. All right, so we're done, right? We're just over. We've finished it. Except, have we? Because I have some questions. Why is P prime longer, right? This is a transaction between you and the reader. You never really told them. That seems like an important point. That's the contradiction. Why is P prime longer? So let's go ahead and add that in, add a reason. So to do that, we could go back and say, let's actually go back and go EQI1 bigger than 2, and hence that actually it's larger than EPI1 over 2. So it's actually at least half of the path P1, the other one's at least half of the path P2. And then we note that E of P prime is the sum of all these things, and so it's at least E of P plus E of P1, which is then strictly greater than E of P1, since E of P is actually at least one edge as they don't intersect. And then if I had a little more space, I would have spelled even that part out, but this at least is doing the work of showing the formula and the equation as to why it's longer. And hence P prime is a longer path than P1. So now we're done, right? Well, there's one last bit. Why is P prime a path? Right? Maybe that was lost in the whole discussion. We just define this thing, let P prime be this. And we just are happy it's contradiction, it's a path. We know it's longer, but why is it a path? So let's stop and pause for a moment and think about that. Okay, so now you're back. So why is it a path? Well, it need not be a path, right? I mean, you could be having this path P, and it could be going through P1 and P2, and so when you add the Q's, then you don't actually get a path. Well, that needs to be fixed, right? To get a contradiction, we need a longer path. So how do we fix that? Well, you add shortest. There exists a shortest path P from V of P1 to V of P2, and since P is shortest, we get that actually, you might as well say that V of Pi intersect V of P is 1 for each I in 1, 2, otherwise it wouldn't be shortest, but we've kind of already said that, so I won't do that and be pedantic. But we mentioned that it's shortest, we mentioned that fact that it only has one vertex, and now you can actually note that P prime is a path in G when you do this construction. And you can spell that out in more detail, but that's at least enough for the reader to get them there. That you've done the shortest, and that's actually the reason that you get a path. And now we've completed our proof. It's all good there, and then we have our theorem, now corrected with the connected version. And actually, maybe as one last point, this is long. I added in equations, which was nice and spacing, so you could read it better, and I hope you appreciate that. But maybe this is a little blocky, so I'll even make another paragraph. And where would you split it? Well, I decided to split it, after we've introduced our p, then we continue on trying to make our p prime by doing this let u's and let q's. That seems a nice place to go ahead and split it into 2 paragraphs. And there's our proof and our writing example. We've turned a poorly written proof into a well-written, at least clear proof. Even if it didn't have maybe every single detail, it had all the relevant details to those questions about why the things were true. And that concludes our lecture for today. Next time we'll pick up when we get in discussing about coloring and the motivation for Brooks' theorem. See you then!